Hi, today I want to talk about distances in signal analysis. Intuitively, the distance between 2 points is how far away one point from another. But life is not that easy. Even with 2 simple points, the question about the shortest distance between these 2 points might get a little bit complicated. If there are no additional constraints, then we can define the distance between x and y as the length of a straight segment connecting those 2 points. We will call it Euclidean distance. Now, imagine that you are in your car and trying to get from junction X to junction Y using the shortest trajectory. But now you are constrained by the city block structure, so you can drive only through the streets, but not through the buildings. You will have to move mostly vertically or horizontally, but this kind of distance is called city block or Manhattan distance, or sum of absolute differences, SAD, and this is different from Euclidean distance. Now, imagine a pilot is planning long flight across the Atlantic Ocean with the shortest distance. This trajectory will likely be a part of a semicircle, and we will call that shortest distance on the surface geodesic distance. As you can see, defining distances between 2 points is not a trivial problem. It becomes even less trivial if we talk about distances between curves or signals. Still, there are properties that are common to all of the descriptions of distances that I mentioned so far. These properties essentially define the subset of distances which are called metrics. I don't know if you have heard about metric or about metric spaces, but this is a very important topic in signal processing. Alright. So let's define what distance or metric is. First, the distance between point X and point X, which is X to itself, is always 0. And this is the only point to which the distance is 0. Second, the distance from point X to any other point is always positive. Third, the distance from X to Y is the same as the distance from Y to X. So it doesn't matter if you are moving from that point to that point, or from that point to that point. Finally, the distance from X to Y and the distance from Y to Z cannot be shorter than the distance from X to Z. We can represent that graphically as D1 plus D2, larger or equal distance D3. This property is also famously known as triangle inequality. Now let's see some examples. I will start with defining a few popular metrics for 2-dimensional space, where each point in space has only 2 coordinates. Let's say we have 2 points x and y, and these points have coordinates x1, x2, and the second point has coordinates y1, y2 accordingly. So let's say we want to define Euclidean distance between these 2 points, x and y. And we can use Pythagoras theorem that the distance dE squared equals sum of the squares of D1 and D2. So we can get the formula for the Euclidean distance as the square root of the sum of squares. For city block distance, we need to compute the sum of absolute differences in both dimensions. The absolute value of y1 minus x1 plus the absolute value of y2 minus x2 will be the difference that we are looking for. Note that it doesn't matter by which trajectory you are moving from point A to point B on a rectangular grid. The distance always will be the same. Another popular distance is the maximum between the absolute difference of y1 minus x1 and y2 minus x2. This distance tells you in which dimension you need to travel the most. Alright, so now we are ready to define metrics for measuring distances between signals. We can think of one-dimensional signal as a list of points or numbers. The list of numbers describes the values of a signal as a function of time or space. And it is called vector in linear algebra. So one-dimensional signal is n-dimensional vector in algebra. How can we define metrics that would measure distances between 2 vectors? We do that exactly the same way as before, but with more points. So the first signal that we call x will have samples x1, x2, x3 through xn. We will have n points. And the second signal y, we will be building it from points y1, y2 through yn. All formulas with the distances will be trivially extended with more dimensions like this. You can pause the video and make sure that you understand how the distances were generalized to more dimensions. As with many other magical things in math, apparently all distances above, and many more, could be written using the same formula. This formula was proposed by Hermann Minkowski, and surprise, surprise, it's called Minkowski distance. By the way, Minkowski is more famous for his invention of space-time, and this is related to theory of relativity, and by the way, also he was Einstein's math teacher. Alright, so get back to our distances. This simple formula, which Minkowski proposed, is defining the new kind of distance, which is generalizing everything we discussed before. Naturally, for p equals to 2, we get Euclidean distance. For p equal 1, we get city block distance. And if p approaches infinity, we technically get distance of maximum. You can choose other p values if you want to, and you can get different distances using the same formula. Because of this formula and the relation to the parameter p, the Euclidean distance is called also L2. L2 distance. City block distance is called L1 distance. And distance of a maximum is called L infinity, or Chebyshev distance. Same Chebyshev from the filters. Okay, here you can see a simple MATLAB function which is implementing Minkowski distance between two simple signals x and y given in the vectors x and y. You might ask yourself, could that be a reasonably defined distance between two signals that would be not a metric, which means it will not follow the rules that we just discussed? The answer is positive. Here's one example. Let's say we have three rivers running from left to right, and we will assume that their trajectory is our signal. It is reasonably to define the distance between two rivers as the minimal distance between the rivers. Note that in this case, the triangle inequality does not hold, because the distance from river X to river Y plus the distance from river Y to river Z is significantly smaller than the distance from X to Z. Finally, to conclude this microlecture, I want to show a few additional popular examples of distances between two signals, mostly related to Euclidean or city block distances. You could pause the video and learn more about them. Thank you very much for listening. If you have any questions or concerns, please contact me. All the details are in the video description below. Have a great day.